This is section 3.3, and this is going to be about the applications of linear programming. So in other words, we're going to get some word problems and choose what we need to set up for a linear programming situation and solve for either a minimum or a maximum. So we've got one example here, and then we've got three problems in the problem set. So let's look at the only example we've got here. It's on nutrition. Certain animals in a rescue shelter must have at least 30 grams of protein and at least 20 grams of fat per feeding period. The nutrients come from food A, which costs 18 cents per unit and supplies 2 grams of protein, 4 grams of fat, and food B, which costs 12 cents a unit and has 6 grams of protein and 2 grams of fat. Food B is bought under a long-term contract requiring that at least 2 units of B be used per serving. Another contract requires that the amount of food B used be no more than 3 times the amount of A. So they've given you a lot of information. So the best way to approach it is to usually make a table. So the question is, how much of each food must be bought to produce the minimum cost per serving? So we are going to minimize this problem. If we let X be food A and Y be food B, so we've got number of units, X and Y, because we don't know that. That's what we're asked to find. Grams of protein in food A, and we get all this from our paragraph, were 2 and Y was 6, fat was 4 and 2, and we were told that you had to have at least 30 of protein. So we have greater than or equal to 30 there, and at least 20 of fat, so greater than or equal to 20, and the long-term contract was Y on food B was at least 2 units of B, so greater than or equal to 2, and the cost 18 cents and 12 cents. So that's how we get. Now, we are trying to minimize the cost. So minimize the cost is what we're trying to do. And that helps you come up with your objective function. So 18 cents times the units of A, so 0.18x plus 0.12y. If we want to minimize the cost, that's our function, z equals that. Subject to 2x plus 6y has to be greater than or equal to 30. 4x plus 2y has to be greater than or equal to 20. And y has to be greater than or equal to 2. And the last part of this said no more than 3 times the food in A. So it has to be less than or equal to 3x. That's the contracts. So if they went down here and they graphed those lines, the constraints, we had y equals 2, we had y equals 3x, that's that thing separated, and then we had 2x plus 6y equals 30, and 4x plus 2y equals 20. So we did that. Here is our region that we're going to look at. We've got 3 corner points. Okay? Corner points are 2, 6, 3, 4, and 9, 2. You test each of those in the objective function. You get 102 is the smallest of those 3 numbers. That is the minimum. So the minimum of $1.02 occurs at 3, 4. That means 3 units of food A and 4 units of food B will produce the minimum cost of $1.02 per serving. Okay? So let's try it on the homework problems. The first problem's really just to get you started. It's pretty easy. Write the constraint below as a linear inequality. And so a candidate will spend no less than $9,900. So that means it's got to be more than $9,900 on radio and TV advertising. Each radio spot costs $130 and each TV ad costs $760. X is the radio spots, Y is the number of TV ads. So I think you could see that 130X plus 760Y has to be greater than or equal to 9,900. So that one's pretty easy. And then we get to one that we have to actually work out. And I'll let you read through that. That's where we're going to get our information. It's about a manufacturing company making engines from 2 assembly plants. So we have plant 1 and plant 2. And all of that information I've organized into this chart. And I just went into Excel and grabbed a table, created a table and did it, but you could draw it out. You don't have to make it that formal. But I tried to get at least that much done. So plant 1 and plant 2, engine shipped to X and to Y. And this says, let's see, the company can send at most 100 engines to these assembly plants. So X plus Y has to be less than or equal to 120. Shipped to just one, or it actually says plant 1 needs at least 45 and plant 2 needs at least 32. So X has to be greater than or equal to 45, Y has to be greater than or equal to 32. Then it talks about the rebate. And they talk about that rebates for plant 1 are 20, so 20X plus 15Y, and they have to be greater than or equal to 1,500. If you're reading the problem, that should be apparent. Cost to ship each, they say 35 to ship to plant 1 and 40 to go to plant 2, so 35 and 40. So the objective function is going to be Z equals 35X plus 40Y. And then we take the rest of these, X plus Y less than or equal to 120. X greater than 45, greater than or equal. Y greater than or equal to 32. 20X plus 15Y has to be greater than or equal to 1,500. In order to graph those, you do need to reorder some of them. And I did that here and here. And I just did this one by hand. I did the next one on the calculator, but I wanted to show you could do some things. You kind of generally sketch it, and you get this region that's enclosed right here. It's right in here. And you have to find the corner points, and I did that by setting things equal to each other. So the 20X plus 15Y equals 1,500, Y equals 32, and substitute the 32 in, and you get X is 51. So I set equations equal to each other, the parts, and got the corner points. I listed those corner points here, evaluated in my objective function, and I was trying to find the minimum. I indeed found that to be 5132. And so when you go back up to the question, 51 going to plant 1, 32 going to plant 2, minimum shipping cost when you plug in 51 and 32 does give you 3,065. So it's the same process, little bit of work here, but same process. All right, let's look at the last question. A dietitian is planning a snack package of fruits and nuts. Each ounce of fruit will supply 0 units of protein, 2 units of carbs, and 1 unit of fat, and will contain 20 calories. Each ounce of nuts will do 3 proteins and 1 unit of carbs and 2 units of fat, and will contain 32 calories. So right here in this chart, I've got protein, carbs, fat, calories down this way, fruits, nuts separately, and then if you package them together. We do get some other information. Every package must have at least 6 protein, at least 10 units carbs, and no more than 9 units of fat. So these two together, greater than or equal to 6, these two greater than or equal to 10, and these two less than or equal to 9. Calories are 20x 32y. And the question asks, what is the least number of calories possible in a package? So we're minimizing calories. So 20x plus 32y, z equals that. That's our objective function. I put all the constraints here from the chart, and I added x greater than or equal to 0 and y. We know we're in the first quadrant. I had to reorder these in order to put them in the calculator, but I did that. And I was using my newer emulator, and I got this overlap right in there. That's my region, my feasible region. I used the calculator to find those intersecting points, and so there was one here and here and here, and I found those by second calc intersect, or you could also do it by hand this way. So I got those corner points. Then I evaluated those three in my objective point function. I plugged those in, and I got these numbers, and we are trying to minimize. So 4, 2, and 144 are the answers that go way back up here. And all it asked for was the minimum. So that was 144. So there's only 3 questions, but each of those does require a good bit of working. So hopefully that will get you started on doing those.